Okay, now we come to now the situation elliptic polarization. This is a most complicated situation, so I don't think I can totally finish that. But let's just start the discussion. So you have epsilon plus amplitude along the plus circular polarization, what we call left polarization, and then plus epsilon minus for the right polarization. Okay, and then the phase vector. Okay, so this is nothing but just decomposing the electric field into these two unit vector of the two circular polarization. Okay, so that is still general. And now we discuss that the most general case is elliptic polarization, but we want to have a notation or some way to discuss in what situation will be the general case elliptic polarization, how does it go back to linear polarization and circular polarization. So now once after we express the electric field in terms of this circular polarization unit vector, we can look at these two amplitude and define a ratio R defined as the ratio of these two magnitude amplitude, which can be complex. Okay, so this can be complex. Okay, so now it means that the magnitude of the first the axis, the ratio of the two axes is defined as it's a little bit difficult to see, but we'll, the ratio in the axis is defined. I mean, it turns out to be the magnitude 1 plus R divided by 1 minus R. So we need to do a little algebra to get to that. But so once you define this ratio, you can express one of that, get the other one out, say like get E plus out of this expression. So like E, you get E plus out of here. Okay. And then that becomes epsilon plus R epsilon minus. Okay. And then the same phase vector. Okay. And then go back to the epsilon 1 and epsilon 2 to get to this ratio, because epsilon plus and minus defined this way. So you substitute this into this one, so you get E plus divided by square root of 2. And then E plus, both these have the unit vector, one, epsilon 1, and both have the same sign, so you have 1 plus R, epsilon 1. And then for epsilon 2, the plus, E plus has a positive sign, plus I, E minus have a negative I. So you have a plus I times 1 minus R epsilon 2. Okay. Epsilon. Okay. And then the phase vector dot x minus 8. Okay. Now this, you see the two axes, the now epsilon 1 and epsilon 2s are real vector, real unit vector. So it means that so if this is epsilon 1, and this is epsilon 2, so the component along the two direction that has the different amplitude. One is 1 plus r, the other is 1 minus r, but both can be complex. So the actual ratio between these two axes, so have this, so this ratio between the length of this axis is different. It's not exactly one. The magnitude ratio is 1 plus r divided by 1 r minus r. It's just from this expression. So it's generally form an ellipse. I mean, this is, we haven't talked about actually the ellipse can actually not just along the xy axis or this epsilon 1, epsilon 2 axis, it can actually make an angle. And we'll talk about how you determine the angle next time. So this is a situation where the ellipse is, the two major minus axes of the ellipse are following along epsilon 1 and epsilon 2, but it actually can be and have an angle. Depends on the phase of R. R can be complex. So, but just by this ratio, you can see that it's a general situation where it's like an ellipse. But it takes a few more lines to see how it rotates at a certain angle. Depends on the phase of R. Okay, we'll do that next time. And then the last case is a general case that we started the discussion. So basically, you can express a general wave like electric field vector. You can either use epsilon 1 and epsilon 2 as a basis. There's a linear polarization basis, or using circular polarization basis, this epsilon plus and minus as your basis. So we basically decompose electric field into two terms. One is E plus, the other is E minus the amplitude in the two polarization unit vector. Okay, so this is general. So any electromagnetic wave, the electric field, a plane wave, the electric field can be decomposed in this form. But generally, you can take the ratio of the epsilon minus amplitude to the epsilon plus amplitude and get defined at R. So the R in general, of course, is complex, but in the special case that R is real, then the situation is that the electric field will rotate as an ellipse in the space of this 1 and 2. I should say, yeah, this is not very good. So this is, I guess this is 1, this is 2. In the two unit vector space back to the linearization, 1 and 2 axis, then it form a ellipse. Okay, so last time we started doing that. I mean, we can do it more explicitly. Say we are just rewriting this form using this ratio and get to this. So that's just pull out the epsilon plus out of here. And then we get back to epsilon 1 and epsilon 2 using the linear polarization basis, epsilon 1 and epsilon 2. So that get to this equations. Okay, then we can now express that as E1 or E2 or let's see what the notation Jackson used, or EX and EY. So okay, so if you take that, so for the special case, the R is real. So this is real. This is there's an I in here. There's the phase vector is complex. So you have this exponential function. Assuming E plus is real, then we can decompose that. If it's not real, then you basically just add a phase in this, so that doesn't matter. So you can write it like EX and EY. So basically, you can write it EX and and epsilon 1 plus ey and epsilon 2. Okay, and then I should say to see the elliptic polarization, how it is formed like an ellipse, you can take the wheel part of E. So you define Ex and Ey that way. So obviously, we took the wheel part. So the first term is wheel. So the wheel part is just basically you are multiplied by the wheel part of this one. So the in the one direction is multiplied the wheel part of this one. So Ex, this implied Ex is this E plus over square root of 2, 1 plus R times the cosine, which is the real part of the exponential factor, k dot x minus omega t. Okay, and then likewise, the y direction, the real part, right? The y part is the E2. So you have I, so you need the imaginary part of that. So the EY will be equals to negative of E plus y squared of 2, 1 minus R and sine k dot x minus omega t. Okay, so you express that in the real situation, then immediately you can say that you will divide this factor 1 over r to the left-hand side, this 1 minus r to the other side, and square those. So that will form that you see is like the equation of the ellipse plus ey over 1 minus r squared. Okay. So you do that, you add the two together. What you have is cosine square plus sine square and divided by 2. So that equals e plus square over 2. Okay, so that's an equation of an ellipse. This is the situation. You put Ex and Ey, or put in the XY space, or epsilon 1, epsilon 2. So we start with a Ex in the X direction. And so this is an ellipse. It traces a ellipse where the major axis and a minus axis is just this divided by this 1 plus r. Okay, so basically you're saying that the major axis, this location is when Ey is 0. So Ex in this case is 1 plus r times this Ex. So this term, this location A plus over square up 2 times 1 plus r. Okay, and this is this distance. And this distance is likewise E plus over square root of 2, 1 minus r. Okay, so that is a situation of an ellipse. Therefore, what we call this is elliptical polarization. So this is a general case, okay, except that we are talking about just a special case that R is 0, R is real. Then we can say that the ellipse has the major and minus axis along x and y, or epsilon 1 and epsilon 2. Okay, so that is, I mean, the polarization is a general case that elliptical is neither linear nor circular. So that in that sense is general, but the axis of the ellipse is special since we assume R is real.
Now the circular polarization is, elliptic polarization is the general case that you have E minus divided by E plus is a ratio. The magnitude is R. Obviously, this is a magnitude, so it's greater than 0. And then a phase of, okay. And all these E plus or E minus can still be compact, but with this ratio, we define this ratio, then obviously the electric field, you can write it as get the E plus out becomes 1. Actually, 1 is E plus R E to the I of E minus. And then the phase, the I X. Wait, that's fine. Last time we said we try to make the two terms symmetric by they basically pull out the E to the I alpha of a 2-factor out of the bracket. And then so this one is, I mean, E plus also can be complex, so it can be a magnitude, and then it can have a phase, so like phi plus, something like that. Like, but this is unimportant. I just write it out explicitly so that so you know that the phase of the magnitude itself doesn't matter. It's the ratio that matters. Okay. And then you pull out another factor I alpha for 2 here. So this becomes E plus times E with a minus I alpha. Because you pull out these factors, you need to subtract this in the exponential function. And then you have the rest is all E minus E I alpha. Okay. And then you have this exponential function. Okay. And the reason these phases 5 plus and the alpha, it doesn't matter now because you combine it with this exponential function, they are all just phase. So it doesn't matter. But then last time we said that we can define this. So this is defined as epsilon plus I. And this one is defined as epsilon minus I. So basically we are saying that we're defining epsilon plus or minus I as epsilon plus or minus times the phase. Now this is minus plus. Okay, so we just define this. If right now it's just define it. We don't know what they are not yet, but we'll figure out what they are later. Okay, so we just rewrite everything. And then this E plus pi. And did I forget? Oh, that's fine. Yeah, that's all. Minus pi. And then everything is in the phase. And then all the phases of this X. Okay, and now we're getting into a situation similar to the first case, but we still need to figure out what those are. So, now we can write it out explicitly. So there's this is a compact one. So this is a compact vector. This is a compact number. So we want to write it in real part and imaginary part. Now, so let's first write it out explicitly. 1, and then plus or minus pi epsilon 2. And that's just using this in here, and then multiplied by this one. This one is just using the Euler relation. It's cosine of 2 minus plus pi. This Euler relation with a minus plus sign here becomes minus plus. Okay, you know all these things, right? All the Euler relation. Exponential function becomes like that. Okay, and now you separate in the real part and imaginary part. Put this back here. The real part has two terms. One is epsilon 1 times this. This is real. This is real. This is real. So it's cosine of 2 epsilon 1. Right? Okay. And then this times it will be real because I times I is minus 1. And plus and minus, plus minus, plus minus. So they all cancel become positive. Plus of epsilon 2. So that's the real part. And the imaginary part is you have plus minus this one times this one is imaginary part because you have I. This is real. So plus and minus I. And let's group the imaginary part like here. So you have epsilon cosine over 2 epsilon 2. And then this times that. And this is minus, but so you have minus sign. 2 times epsilon. Okay. Let's just say this stay here. Okay, so this is just basically write out the real imaginary part explicitly. And now we try to identify the physical meaning of this real part and imaginary part. So that's basically just geometry. Okay, so geometry is like draw it like epsilon 1, epsilon 2 axis. Okay, and now we claim that we just define an angle alpha over 2 with the epsilon 1 axis. And now these are unit vector, right? So you can draw a unit circle. So the radius is 1. So now you look at this point. This point has a epsilon component. It's this is just 1. So this length is cosine alpha 2 in the epsilon 1 direction. And this projection on the epsilon 2 axis is sine alpha over 2, and so this length is sine alpha over 2, and that is along the epsilon 2 direction. We see that this one has the component cosine alpha 2 in the epsilon 1 direction. This one sine alpha over 2 in the epsilon 2 direction. With this vector is epsilon 1. Okay, so it's the geometry. Fine with you. Okay, and likewise this one. Now you draw a line perpendicular to here. So this is alpha for 2. This is alpha for 2. Now again, this point. You look at it, it has a projection along epsilon 2 for cosine alpha over 2. So this one has this component. And the projection along epsilon 1 is sine alpha 2, but on the negative side, so it's minus sine alpha, minus sine over 2 epsilon 1. So this is epsilon 2. Okay, with this epsilon 1 pi, epsilon 2 pi is what we define. So that this, so if we define it by this geometry, so this is of epsilon 1 pi plus or minus pi epsilon 2 pi. Okay. So this definition is exactly like this one, except that you are using epsilon 1 pi and epsilon 2 pi rather than epsilon 1 and epsilon 2. And these two unit vector are rotating from epsilon 1 and epsilon 2 by an angle alpha over 2. So basically, you rotate your coordinate system by angle alpha over 2. And you define your unit vector by after you do the rotation of your coordinate system, the unit vector becomes epsilon 1 pi, epsilon 2 pi. And you combining that, and that you get the spherical or circular polarization unit vector epsilon plus or minus pi that is based on this rotating coordinate. Okay, so now you identify this these two epsilon plus epsilon minus pi just as a circular polarization unit vector. And so this, you go back to the first situation. So the first situation is the ratio is just alpha with, I mean, just R, just a real number R without a phase. So now the second situation, you have a phase where you can move the phase out and rotate your coordinate system such that you go back to the first situation. And you remember this first situation is that the situation is you have a, let me draw. Along this new coordinate system, the polarization is elliptic polarization with an ellipse that is already have a circle, so I just draw arbitrary ellipse. With the principal axis along this epsilon 1, epsilon 2 direction. So this is the ellipse, and the ratio between the length of the two axes. This is 1 plus r. So like a proportion of 1 plus r along this axis. And along this axis, this length is proportional to 1 minus. Wait, remember that that is the picture. Yeah, just right now. Just didn't right now. So, but anyway, so that's what we figured out last time. So 1 plus r. So the ratio is 1 minus r divided by 1 plus r. Jackson or the other way around. On the out. Okay, so that this means adding a phase means that it's still elliptical polarization, except that the principal axis of the ellipse just rotate, and it rotate by an angle not alpha, it's by alpha over 2. Okay, so instead that is important because there will be a homework problem. I'll post that today, maybe today or over the weekend. And there'll be one question that you use, and you see that the rotating angle, and that one actually is I mean, it can be a circular polarization or elliptic polarization. But if you have circular polarization, but the phase velocity between the plus or minus polarization is, if they are different, mean that the phase angle is changing with time, then you see that the rotating axis actually change, even if it is a linear polarization. Because a linear polarization, you can always decompose in two circular polarization. And if you have a linear polarization, then if it's original along epsilon 1, but then as it propagates, this principal axis actually keep changing, and the angle just keep moving. And that is the situation in possible, one kind of possible way. The right-hand circular polarization, the left-hand circular polarization wave, and they are not propagating with the same dispersion relation, and so the polarization axis change, and that is called the Faraday rotation in plasma physics. So there will be a question asked you to figure out that the rotation, and what that depends on the phase, whatever the dispersion relation is given. Okay, so we work on that, but that is the formula that you can use whenever you see the ratio between them has a complex number with a phase. Then this means we rotate from the original axis by angle alpha over 2. Okay, so that is something you can use. Okay, and to figure out this Faraday's rotation. All right, so up to here, any questions?